And so the lecture is divided into parts. One is about magnetic interfaces, essentially describing magnetic phenomena that occur in systems of reduced dimensionality. So in particular, magnetic thin films and nanostructures that are then relevant to understand also spintronic effects. So what you see here is just a selection of topics. Of course, there are others, in particular, for example, dynamic effect that will be treated by Burkhard Hillebrands in the next lecture. So I just restricted myself to, in the first part, to essentially fundamental magnetic interactions and magnetic moments, magnetic anisotropy. And all this is at a very introductory level, so assuming not much in terms of previous knowledge of beyond classical electromagnetism and some quantum mechanical notions of magnetic moments. And then I will move on to a description of transport effects generated by electric current injection in magnetic conductors. And so then we deal with spin transfer torques, spin orbit torques, and what we can do with these torques. Magnetism is a very interesting branch of physics, material science, and chemistry as well, because we have the interplay of both composition and structural effects, as well as external agents like temperature, magnetic fields, electric fields, currents, etc. And all these effects determine the overall magnetic response of systems, and we have therefore also many ways to tune the magnetic response by playing with the composition of materials, their size, as well as with external stimuli. So why is this interesting? From a practical point of view, we have the possibility to build better magnets, either hard permanent magnets or soft magnets, for many applications in electromechanical engineering, for example. And it's interesting to notice that even the tuning of hard permanent magnets is based on a very deep understanding of the micro and nanostructures of these systems. For what we are concerned, so systems with that are essentially interfaces or surfaces or nanostructures, then we know that small magnetic bits are used as recording media. We know that magnetic layers are used to fabricate sensors. There are also interesting phenomena that emerge that are not found in bulk systems when we combine different materials and tune their dimensions as well as proximity effects. And eventually what we will focus on at the end of this talk is on the electrical control of the magnetization in small devices. So I'd like to start really from the basics. So to notice that we have magnetic moments that survive in some of the metal elements, in particular in the 3D metals, iron, cobalt, nickel. And the spin magnetic moment that survive in these materials, right, are due to the unbalance between the field and unfilled majority and minority spin states. And here you see a pictorial representation of the density of states for spin up and spin down electrons. So the difference in the filling between the states gives us, this is the number of holes in the d band. This is roughly proportional to the spin magnetic moment, which is mostly a property of the localized d orbitals. And as you see, there is a difference between the spin moment expected for gas phase atoms. This is essentially given by the first Hons rule, and the spin moment that is actually measured in bulk metals. Okay. So when we deal with magnetic thin films and nanostructures, we essentially occupy the space in between the bulk limit and the single atom limit. Okay. This is also true for the orbital moment, which, however, is more strongly reduced than the spin moment in thin films and nanostructures. So it is also important to notice that the amplitude, the magnitude of the magnetic moment in a metallic system is proportional to the exchange splitting, which is schematically depicted here. So this is the difference in energy between the sort of a center of gravity of the spin up and spin down density of state. And so the larger this exchange splitting, the larger the imbalance between spin up and spin down electrons. And so there is really a nice correlation between magnetic moment per atom and exchange splitting, as you see in this plot here. So we expect that whenever we modify the density of states, then we will also modify the magnetic moment. And this is in fact the case because as we go from a bulk system, here you see the bulk density of states of iron calculated by ab initio method. You see that this density of states, which is essentially due to the d bands, extends over let's say several electron volts, about 5-6 electron volts for iron. However, if we consider iron thin films, as we have here for a monolayer of iron on a gold substrate, right? We see that this density of states is now narrower. So we have more states that are confined in a narrower energy interval. And that if we further reduce the dimensionality of the system, so if we go to single iron atoms on this gold substrate, this density of states is really now even more narrow and peaked. And this narrowing, which is due essentially to the reduction of the atomic coordination. Right? So we go from a sort of a band-like system towards an atomic-like system with discrete states. And when this occurs, this narrowing of the bands also implies a shift of the bands, and so typically the minority bands shift towards higher energy to maintain charge neutrality in the system, and then the imbalance between spin up and spin down state increases. So we expect stronger magnetic moments in systems with reduced dimensionality, and in fact this is also what we expect from this simple plot here. So we expect to be somewhere in between these two curves. Okay. And indeed, this is reflected both by calculations and measurements. Here I report two cases. This is an ab initio calculation of the magnetic moment at the surface of an iron crystal. Okay. And it turns out that the magnetic moment is actually larger in the topmost surface layer compared to the bulk layers. Okay. And this increase of magnetic moment also depends on the crystal phase, because it is essentially an effect driven by the lower coordination of the surface atoms. And therefore, surfaces with different coordination experience different enhancements of the magnetic moment. Okay. So this is the ideal case. Now, of course, if you try to measure the magnetic moment at the surface of a crystal, right, you have to do this in ultra high vacuum, otherwise contamination effect will most likely decrease or destroy the magnetic moment of the topmost surface layer. Now, similar effects are also found for thin films. So thin film is a magnetic layer deposited onto a non-magnetic substrate. And so in general here, both the layer at the interface with the substrate and the layer on top can have different magnetizations. And this magnetization can also be larger typically for lower coordinated atoms it is larger, but for atoms at the interface you can have either an increase or a reduction of magnetic moment. For the system depicted here, this is an iron layer deposited on a tungsten substrate capped by silver. These are most Bauer measurements that show an increase of the magnetic moment of iron relative per atom relative to the bulk limit here. So this difference here is due to this enhancement of magnetic moments at the interface. Regarding the orbital moment, now here we have similar considerations in terms of density of states. So if we consider a gas phase atom, we have orbital states that are split according to the orbital number. Okay, and the second Hund's rules tells us, so first of all, the first of Hund's rules tells us that all the spin up states will be occupied first, and then all the spin down states will be occupied. But then the second Hund's rules tells us that the system maximizes the orbital angular momentum, and this means that these orbital states are occupied in sequence, essentially. So for this is a diagram for a system with 7 electrons, like a cobalt D7 ion. We expect an orbital magnetic moment of about 3 Bohr magnetons. Okay. However, when the metal is formed out of cobalt atoms, these states are broadened by electronic hybridization effect. And so the orbital moment is actually smeared out. Okay. This is a purely electronic hybridization effect. And on top of that, we have a so-called crystal field quenching of the orbital moment, which is also occurring in magnetic insulator, and it's a very important and strong effect, which tells us that depending on the symmetry of the crystal field, the atomic wave functions that have a net orbital moment will actually combine so as to form this real wave functions. These are the real crystal harmonics. And if you then consider the expectation value of the orbital moment operator in such states, these are the typical d orbital states, you'll find out that these states are made of a composition of opposite orbital momenta, and so the orbital magnetic moment is actually 0. Okay. You can also see this because in order to have a net orbital moment, you need electrons that circulate, right? That perform sort of circular orbits in the plane. And if you have crystal field, then the charge distribution actually becomes a standing wave. It's adapted to the symmetry of the crystal, and so you do not have any more an orbital motion of the electrons in this sense. So this was a density of states picture, but of course we can also, instead of starting from bulk materials and seeing what happens when we reduce the dimensions of a magnetic system, we can also do the opposite, start from an atom and see how the moments change as we add more atoms together. Okay, and this leads us essentially to the same conclusion. So if we start from a gas phase, cobalt atoms, as you see here, these are the Hund's rule magnetic moment, maximum spin, maximum orbital moment, right? And then as soon as this atom is deposited onto a substrate, even a non-magnetic one, these moments are going to change. We have also symmetry breaking here, so we expect magnetic anisotropy to occur. And all these quantities are going to be affected by the coordination of these atoms. So if we have clusters or nanoparticles, single layers, multi-layers, we expect strong changes in the magnetic properties. Okay. This can actually be measured. These are schematics of measurements that we performed on cobalt atoms deposited on a platinum 111 surface. And we see that starting from, so compared to the gas phase behavior here, where we expect large spin and orbital moments, we measure a reduction of both the spin and orbital magnetic moments. We have an onset of magnetic anisotropy for magnetization measured out of plane or in plane. And then these moments, in particular the orbital moment, further reduce upon increasing the coordination of the magnetic atoms on the surface by forming larger clusters. The anisotropy also reduces, and this then continues in thicker films and bulk systems. Now, what is important also is spin-orbit coupling, because what we have seen so far are spin and orbital magnetic moments that essentially emerge from this term in the Hamiltonian of electrons in an atom that orbit around an atom, right? So if we have the usual terms, this is the Hamiltonian in the central potential approximation that gives hydrogen-like orbitals. But then the electronic correlation effects, these are the ones that justify the Hund's rules. The first and the second Hund's rules are basically ways to minimize electron-electron interactions. And then, of course, we can include also the Zeeman interaction. But there is another interaction which is very important that then justifies the third Hund's rule, and this is the spin-orbit coupling, right? The coupling between the orbital and spin moment, okay, which is can be seen as essentially the orbital magnetic moment that precesses due to the magnetic field produced by the spin magnetic moment or vice versa. And it turns out that in an atomic system, this coupling, which is exemplified by a spin-orbit coupling constant, is then proportional to the gradient of the electrostatic potential at the position of the electron. So it's something that also depends on the nuclear mass of the atom. Now, this is important because the orbital moment, as the name says, comes from the orbital wave functions, and so it is inherently related to the symmetry of a crystal lattice, whereas the spin moment per se is an isotropic quantity. So the spin-orbit coupling links the spin magnetic moment, which is actually the largest one in solid-state system, to the orbital moment, and so it links the spin magnetization to the lattice symmetry. And that's important not only for example, establishing magnetocrystalline anisotropy, but also to allow the magnetization to relax, because we need to exchange energy between the spin reservoir and the lattice reservoir, and this can be done only through spin-orbit coupling. So in terms of energy, electron volts per atom, this is a very small coupling term. In a 3D metal, we have about a few tens of milli-electron volt per atom. So it's really smaller compared to the bonding energy and also the exchange energy that promotes the formation of the spin magnetic moment, for example. It's small, but has an influence on many different effects. For example, it determines the magnetocrystalline anisotropy. It determines the Jałodziński-Moria interaction, which is a non-collinear magnetic interaction that is important in both bulk systems, in particular bulk antiferromagnets, as well as interfacial systems, including ferromagnetic interfaces. It's important to establish magnetic damping. And it's also important in transport effect because spin-orbit coupling is at the origin of the anisotropic magnetoresistance, the different types of Hall effects, as well as the so-called rush by Edelstein effect. We will see some of this later. So now I'd like to comment on magnetocrystalline anisotropy because that's a very fundamental quantity especially for small magnetic structures. So we have a situation in which the symmetry of the orbital wave functions determines, and also their hybridization determines the magnitude of the orbital magnetic moment. Okay, this L here. Okay. And so the orbital magnetic moment somehow has different values, different expectation values, depending on the direction relative to the crystal axis. So you can have a situation where you have a smaller orbital moment along one axis and a larger one along the other. So now, if that is the case, because of spin-orbit coupling, then the spin magnetization will also tend to align either parallel or anti-parallel to the direction with the largest orbital magnetization. And so this defines the easy direction of magnetization in a crystal. Okay. So, and that's when we talk about magnetocrystalline anisotropy. Now there are models that are used to relate this anisotropy energy to the anisotropy of the orbital moment. It's actually, in the simplest model, that is proportional to the magnetocrystalline anisotropy energy is directly proportional to the anisotropy of the orbital magnetization through the spin-orbit coupling constant. I will not go into this model in detail, but you can find the reference here if you're interested. So that explains the magnetocrystalline anisotropy in different materials. Here you see for the bulk 3D metals, we have different easy axes that also depend on the symmetry of the system. And the magnetic anisotropy energy is typically expressed in terms of this anisotropy energy constants that are either expressed as energy per unit volume or energy per atom, which are relatively small in bulk systems. However, in systems with lower dimensionality, and here I come back to the example of single cobalt atoms on a platinum surface that I introduced before, and going then towards particles. These are two-dimensional cobalt islands with increasing density. We can measure in this systems both the orbital magnetic moment using a technique that is called X-ray magnetic circular dichroism, as well as the magnetic anisotropy energy, for example, by fitting magnetization curves measured with a field applied out of plane and in plane. And we see that there is a strong correlation between the two. So the single atoms have a very large orbital moment, so about 1 Bohr magneton, which is 3 times less than in the cobalt gas phase atoms, but 10 times more than in the bulk of a cobalt crystal. And as soon as we increase the coordination of the cobalt atoms, this orbital moment decreases. This is due to this hybridization and crystal field effects. And we see that the magnetic anisotropy energy per atom follows essentially the same behavior. So this shows very clearly the link between orbital magnetization and magnetocrystalline anisotropy energy. And it shows also that in systems with reduced dimensionality, right, this anisotropy energy per atom increases almost exponentially with the dimensions of the system. So these are the zero-dimensional single atom limit, and this is one-dimensional atomic chains, similar to the system you see here. This is a monolayer film, and this is a bulk crystal. And that this magnetocrystalline anisotropy energy is really important because it is what determines the stability of the magnetization in the system, right? So how hard it is to reverse the magnetization. Here I show that also in thin films, the orbital magnetic moment can be anisotropic. Okay, this is essentially because of the different hybridization of the cobalt wave functions at the interface with a gold substrate. So this leads to a larger hybridization between cobalt and gold orbitals, which spreads the bands of the formed by the orbitals that have out-of-plane symmetry. Okay, so this gives a large density of states for the states that have that extend perpendicular to the interface, and a smaller density of smaller bandwidth for the states that extend parallel to the interface. And because the orbital moment is then proportional to the inverse of the bandwidth, right? This is the more atomic-like picture. We have a stronger out-of-plane orbital moment than in-plane. And this gives this anisotropic behavior. Good. So I see I'm running out of time, so I should speed up if I want to go to the next section. So in short, for magnetocrystalline anisotropy, depending on the bonding configuration, symmetry of the crystal, we can have different magnetocrystalline anisotropy terms that favor either out-of-plane or in-plane magnetization, depending on the crystal symmetry. There is, however, another term that is important in determining the magnetic anisotropy, and this is the dipolar interaction. So whenever we have two magnetic moments, their interaction is anisotropic. So one moment feels the magnetic field produced by the other moment and vice versa. And the interaction energy is given by this dipolar term here, which depends on the relative orientation of the two magnetic moments. Okay. And so as we know, it is easier to arrange dipoles with head-to-tail alignment. So this is the configuration preferred if you have magnetic moments that are aligned on a line or on a plane, right? But if you force the magnetic moment to say, then be oriented as you see here, then the dipolar field favors anti-parallel alignment of the magnetization. So this dipolar, or they're also called magnetostatic interactions, are very important to determine essentially the so-called demagnetizing field, which is the field that a magnet exerts on itself due to these dipolar interactions. And this demagnetizing field is such that it favors, for example, the orientation of the magnetization along the long axis of an ellipsoid or along the plane of a thin film. So if you combine this dipolar interaction, which gives a magnetic anisotropy that is called a shape anisotropy, together with the magnetocrystalline anisotropy due to the anisotropy of the orbital moment, then you get a competition between the two. And so in a generic thin film, where you have certain number of layers that you can consider as a volume layers, so similar to their properties are similar to what they would have in a bulk system. Then you have some interface layer. Then the effective anisotropy energy of this system will be in part determined by the magnetocrystalline anisotropy of the volume part, in part by the shape anisotropy. This is the dipolar term that favors in-plane magnetization, and then by an interface term that scales as 1 over the thickness of the system. And so if this interface term promotes perpendicular anisotropy, whereas this term here usually promotes in-plane anisotropy, then, and this term scales with the volume of the system, right? This with 1 over T, then you typically have a situation where at low thickness, as you see here, a magnetic layer may have perpendicular magnetic anisotropy. This is called PMA. And at high thickness, the dipolar term prevails, and you have a transition to in-plane orientation. And this is quite typical of thin films. What is also important is that because the magnetocrystalline anisotropy depends on the orbital wave functions, and the orbital moment depends on the filling of these wave functions, then by changing the number of electrons that fill certain states, you can actually change the magnetic anisotropy energy. And this can be achieved in practice by gating. So by applying an electric field to a thin magnetic layer. Now, the layer has to be thin because, as you know, electric fields are screened very rapidly in metals, but the interface layers are affected by the electric field. So you have some charge transfer in the interface layers, and this charge transfer modifies the anisotropy energy, which in turn modifies, for example, the coercivity, the magnetic coercivity. You can see we can even go in some systems from a system with out-of-plane magnetization to a system within plane magnetization and vice versa by applying an electric field. And because the anisotropy, magnetic anisotropy also determines the stability of a magnet, you have an effect also on the ordering temperature of these thin layers. Okay, here I should talk about magnetic domains, but if I do that, then I'm going to lose the remaining time. So how long should the lecture last, Michael? 1 hour sharp, or?
Yeah, it should be around 1 hour, and then there will be room for questions.
Okay.
But might be a little bit longer, not sharp.
Yeah. If you extend it by 10 minutes, it's fine, but we don't want to extend it.
I'll try to do maximum 10 minutes more. Okay. So this dipolar interactions are also responsible for the formation of magnetic domains. Okay. Because by forming magnetic domains, the system minimizes the dipolar interaction, the so-called magnetostatic energy, and so the magnetic field lines close on themselves, so we have a minimization of this dipolar energy. However, by forming domains, we have to form domain walls, and there is an energy cost due to exchange and magnetocrystalline anisotropy, which then balances the gain in magnetostatic energy. And that explains why, for example, if we have very small magnetic particles, the system tends to be in a monodomain state because the dipolar interaction integrated over the volume is not strong enough to induce the formation of a domain. However, if the system becomes large enough, then it becomes favorable to pay the energy cost of forming a domain wall here and splitting the magnetic configuration into domains. Okay. And so one can also calculate the so-called critical single domain radius for spherical particles. That's just a sort of an instructive example. Okay. And this is also observed in real systems, that when you reduce the size of a magnet to nanometer dimensions, then really the system tends towards a single domain. Okay. Another important fact that one has to take into account when dealing with magnetic thin films and interfaces is the fact that magnetic order is affected by the dimensions of the system. And that is essentially because the exchange interaction, when it is summed over all the magnetic neighbors, right, you can very well see that if the number of neighbors is reduced, right, this total exchange energy will become smaller, and so the tendency towards magnetic order will also decrease. Okay. And so we expect that this typical magnetization versus temperature curve that expresses the formation of magnetic order at low temperature and the disappearance of magnetic order above the Curie temperature will be affected by the dimensionality of the system. This is in fact the case in thin films. It is found that as one reduces the thickness, here is an example for nickel layers on copper from, say, 6 monolayers is already a Curie temperature that is way below the bulk Curie temperature of nickel. And then if you go to a monolayer, it's even lower, right? So that one has to take into account. Also, the critical behavior given by this exponent here depends on the dimensions of the system. This can be explained in a mean field model where the so-called Weiss field or the molecular field is proportional to the exchange per atom times the number of nearest neighbors. And so if the average number of nearest neighbors decreases as it does in a magnetic layer with non-magnetic neighbors or vacuum, then you expect a dependence of the Curie temperature on 1 over the thickness of the magnetic layer. This is, in fact, also experimentally verified in many systems. And then, on top of this, there are strange things that occurs in interfacial systems. For example, you can find materials that are, textbook ferromagnets like iron that in monolayer forms on certain substrates like tungsten form an antiferromagnetic lattice. And this is because the atomic lattice spacing is actually changes, and then this in iron induces a transition to an antiferromagnetic state. And also at interfaces you have symmetry breaking, and this favors the formation of non-collinear magnetic structures like spin spirals or even skyrmions. And these are due to the Jasinski-Morier interaction that comes from the symmetry breaking together with spin-orbit coupling in this system. So interfaces with strong spin-orbit coupling usually display also some unusual non-collinear magnetic configurations. Okay. I'll skip this. And I don't know if there are questions on this part, or I should move on to the second one. All right.
I cannot see any questions, so I think that you can move forward.
Okay. So this that I presented until now is an overview of magnetic properties of systems with low dimensions. Now we would like to see how these systems are actually employed in applications. Okay. And here I have two examples. They're by no means the only ones. But we know, for example, that magnetic multilayers are used in sensors to read the magnetization. For example, this is a track where we have magnetic bits written in up and down domains, the magnetization in each domain representing a 1 or a 0 of a digital bit. And their state can be written by applying a magnetic field with this right head, okay, with an external coil essentially. And it can then be read by a giant magnetoresistance sensor or a tunneling magnetoresistance sensor. And that's a very compelling application for magnetic films, not only in hard drives, but also in all sensors that, for example, sense the position of a system based on a magnetic, based on magnetic fields. And then we have memories that are random access memories that are based on magnetic tunnel junctions. These are also very interesting applications for this system. And more recent applications that are being discussed in literature are essentially combinations of logic and memory functions, or different types of computing schemes and architectures like probabilistic computing, neuromorphic computing for AI networks, wave computing. Maybe you'll hear something about this in the next talk. Now, why is this relevant in terms of memories? Because if you look at how a memory is organized in a computer, we have at the bottom, the big data are stored in the larger memories. These are non-volatile and usually magnetic, right? And then as we move towards the faster memory closer to the CPU, then we have semiconductor-based memories. These have to be very fast, but they're usually non-volatile. And that means that a lot of energy is wasted just by, even when the computer is idle. right? They need to be refreshed all the time. So there are many efforts that aim at replacing some of these memories with magnetic random access memories. Just skip them. Okay. So here, what one would like to achieve is a non-volatile, fast, scalable memory with that should also withstand many read and write cycles, should be low power, should be cheap. Okay, so this is asking a lot, of course, and not all of this is always possible at the same time. So this is why we have different types of memories for different specific applications. Okay. And there are, of course, many material and engineering issues that go together. So let me first explain the basic principle of a memory based on a magnetic tunnel junction. So here you have a device that is formed by two magnetic layers that are separated by a non-magnetic layer. And one layer has a fixed magnetization that is called the reference layer. Another one has a free magnetization, so that can be switched between one orientation and the other. And so this forms a parallel or an anti-parallel magnetic configuration. And you can decide that the parallel configuration represents a 0 state and the anti-parallel a 1 state. And you can also probe this by performing a magnetoresistance measurement. So most often a tunneling magnetoresistance measurements, which gives a low resistance for the for the parallel state and a high resistance for the anti-parallel state. And so this can be measured electrically by passing a current. And then what is relevant is how can we write the free layer magnetization also using an electric current, right? Because we do not want to use a magnetic field because this is a non-scalable approach. We want to inject the current directly into the magnetic structure in order to achieve switching. This makes it faster, more scalable, and eventually also cheaper. So the point is how to achieve this, okay? And in order to see how this works, we have to check this. Yeah. So we have to consider the conduction of electrons that are spin up or spin down, right? So in a normal metal, normal means non-magnetic metal, generally spin up and spin down states are degenerate in energy, and the conduction electrons are composed in equal proportional by spin up and spin down electrons. However, in a ferromagnet, this is not the case anymore. In a ferromagnet, we have that the density of states are split between spin up and spin down electrons. The main splitting is between the d electron states. Okay. However, the s electrons that are responsible for conduction also feel somehow the filling of the d states, because scattering processes are more likely to conserve the spins. And so electrons with a minority spin orientation, like you see here, they can scatter from an S to a D state because there are empty states available in the minority band here, which is not possible for the majority band because the D states are all filled or mostly filled. So that means that minority spins scatter more than majority spins. And so then we have this so-called two-channel model where we can consider spin up and spin down electrons as having two different resistivities. Okay. So in a ferromagnet, mostly the majority spins that have magnetic moment aligned along the magnetization direction, they have a higher conductivity. Okay. So when a current from a non-magnetic metal is injected into a ferromagnet, you have a spin filtering effect. And so some spin down electrons are reflected and only spin up electrons are transmitted. So we're effectively injecting a spin current that is a difference in number of spin up and spin down electrons. Okay. And this spin current corresponds to essentially a magnetic moment that is entering, a non-equilibrium magnetization that is entering into the system. So this reflection of spins, this transmission of spins, essentially induces a non-equilibrium magnetization at the interface between a normal metal and a ferromagnet. This is also called a spin accumulation. Okay, and the divergence of the spin current corresponds to a change of this non-equilibrium magnetization. Now, what happens when we inject a non-equilibrium magnetization into a magnetic layer? The spins of the conduction electrons will interact with the spins of the magnetic moment in the magnetic layer through the so-called SD exchange interaction. And so the two spins eventually will tend to align themselves. So there is an effective exchange field acting on the non-equilibrium magnetization that is aligned with the local magnetization in the ferromagnet that corresponds to a torque, and an effective exchange field acting on the local magnetization that is parallel to the non-equilibrium magnetization. So you have essentially a mutual interactions between this non-equilibrium and equilibrium magnetizations, and and the change of one is equal to minus the change of the other due to conservation of angular momentum. So that means we can exert a torque onto the magnetization of the ferromagnet by injecting a spin current that generates a non-equilibrium magnetization inside the magnet. And now this torque can actually be decomposed into two torques with different symmetry. Okay, essentially because the only part of the spin accumulation that matters is the one that is this delta M that is orthogonal to the magnetization in the ferromagnet. That's the one. This delta M is the one that is going to produce a net torque according to this equation. Okay. And so there are two components of this delta M that are orthogonal to M. Okay, and they can be vectorially expressed in this way. Okay, with this vector product. So these are two vectors that are orthogonal to M. And so this corresponds to two different components of a torque, of a spin torque. Okay. One is called a damping-like torque. The other one is called a field-like torque. Field-like because this torque is like, you can see this as being due to the exchange field felt by M due to the non-equilibrium magnetization, small m here. And this one has the symmetry of a magnetic damping, so it's called a damping-like torque. Then, of course, different people call it different names, and so here I listed some of the other names that are given in the literature. Okay. Now, how can we understand the actions of these torques on the magnetization? So imagine you have non-equilibrium magnetization entering into a magnetic material with magnetization capital M here. Then this transverse part of the magnetization is absorbed due to the reflection of spin down electrons at the interface with the ferromagnet and transmission of spin up electrons inside the magnet that will be eventually scattered and absorbed. And so this corresponds to a transfer of magnetization from the non-equilibrium magnetization to the local magnetization. So to this torque here. That's the action of the damping-like torque. This is called AD, sometimes it's called anti-damping. The field-like torque, as I was saying before, can be seen as the result of the local magnetization precessing around the non-equilibrium magnetization direction and eventually trying to align with it. And so this is the action of the field-like torque. And this is to mention that you can also have the reversed effect, the reciprocal effect. So if you generate a motion of the magnetization in a magnet, then this will inject a spin current in an adjacent non-magnetic conductor. Okay. This effect is called spin pumping. Okay, so this spin torques effect can be used to drive magnetization dynamics. Okay. And because, for example, if you inject a spin current such that the damping-like torque opposes the magnetic damping in the system, that is why it's called anti-damping, then the magnetization will start precess around the equilibrium orientation. And for a sufficiently large injected current, the precession amplitude will increase and eventually lead to a magnetization reverse. This is a Microspin picture, and this has been seen already many years ago, both in terms of magnetic oscillations induced by spin current injection in this kind of mechanical point contacts, or in pillar devices like so-called spin valves, where one can achieve also reversal of the magnetization. Okay. Now, these are the so-called spin transfer torques. So these occur when we have magnetization, so a current that is passing through a reference magnetic layer. It becomes spin polarized. It then travels through a non-magnetic layer that can be, for example, copper, or it can be a tunnel layer like magnesium oxide. And then this spin polarized current enters into the free layer and generates a spin torque that is called a spin transfer torque, because we are transferring spin momentum from the reference layer into the free layer. Okay. But there are also alternative methods to generate spin torques that are based on spin-orbit coupling. And here really we close the circle between current, that means displacing the electrons in k-space, which means also that we're changing their orbital motion, and then we connect again to the spin magnetization through spin-orbit coupling. Okay. And these effects that would go under the name of charge spin conversion are driven by spin-orbit coupling and can be used to exert spin torques, so to switch or oscillate the magnetization, can be used also to sense it, and can be used also to couple magnetizations. There are two major effects that can be used to generate a non-equilibrium spin accumulation by injecting an electric current into a system. One is called a spin Hall effect. The other one is called the Rush-by-Edelstein effect, or spin momentum locking. The spin Hall effect is essentially the separation of spin up and spin down electrons due to spin-dependent scattering. And this is a relativistic effect that generates the accumulation of spins on the sides of a conductor. So on this side you will have predominantly up spins, on this other side you will have predominantly down spins. And yeah, I can show how this works here. Okay, this can be seen either as a sort of a Mott scattering effect, and it's called the extrinsic spin Hall effect, or as an intrinsic band structure effect that is related to Spinorgic coupling and to the fact that electrons that hop between different orbital states as they move from an atomic site to another, they will acquire a given quantity of orbital momentum that depends on the orientation of their spin, and that deflects them in different ways. So they acquire a so-called anomalous velocity. So that's for the spin Hall effect. We then have the Rashba-Edelstein effect, which produces a non-homogeneous spin polarization perpendicular to the direction of motion of the electrons in the system. And in order to have that, you must have a system, and typically these are interfacial systems, where there is an electric field, a net electric field between two layers, maybe because of charge transfers between the two layers. This electric field is seen by the traveling electrons as a magnetic field due to a relativistic Lorentz transformation. And this effective relativistic field aligns the spin parallel to the interface plane and orthogonal to the current, and essentially produces a non-equilibrium magnetization that can then be used to generate a spin torque. Okay. This can also be seen in K-space, as in this diagram. Good. A very similar phenomenon occurs in topological insulators, where you have states with spin momentum locking. So now, when you have spin accumulation due to one of these effects, here I use the spin Hall effect to show this, right? We generate a non-equilibrium magnetization at the edges of a conductor, which can also be seen as a spin current propagating towards the interfaces of the conductor. This, the amount of spins generated, or if you want, the amount of spin current generated per charge current, this is the so-called spin Hall angle. And in a typical system like platinum, is the order of 10%. Okay, and we have the accumulation of spins at the edges over a distance that is called the spin diffusion length, that is about a few nanometers. Okay, there's some discrepancy on how large this is in different systems, but the order of a few nanometers in metals. Okay. And then this current-induced spin accumulation can be used to generate spin torques. Now they're called spin orbit torques because the origin of the non-equilibrium magnetization is a spin orbit coupling. It's not spin transfer, as I've shown before. The spin torques can be used for switching. They can be used to induce oscillations, even high-frequency oscillations in a magnetic system. And they can be used to induce magnetoroesistances as well as magnetothermal effects. So here I wanted to show some applications of this. Now my time is almost over, so I'll go very quickly about this. So one can, by exploiting current injection in a heavy metal layer, which has a strong spin orbit coupling and therefore produces a large spin Hall effect as well as large Rashba-Edelstein interfacial effects, one can exploit this interfacial spin accumulation to generate a spin torque, okay, because again, this non-equilibrium spins will be absorbed in the ferromagnet, creating a damping-like torque, and will also exert an effective field, creating a field-like torque in the ferromagnet. And so then if the current injected is strong enough, then you have enough non-equilibrium magnetization to produce a strong spin torque and reverse the magnetization in this system. And this can be done in a single layer system and can be done for systems with out-of-plane or in-plane magnetic anisotropy using very common materials. Okay. And the reason for switching can be seen as this. So if you create a spin current that is oriented in plane, when this spin current is absorbed, this corresponds to a change of angular momentum, so to a torque in the same direction as the spin polarization. This torque corresponds to an effective field that tends to rotate the magnetization in a macrospin picture. And so in such a system, the injection of a current will tend to rotate the magnetization over and over. If you then apply constant in-plane magnetic field, you essentially stabilize one direction because you counteract this current-induced field and destabilize the other, and this induces deterministic switching. There are also ways to get rid of this external field to control this effect. In terms of microspin dynamics, this gives this sort of trajectory here. You have the magnetization starts from an up state. As the current pulse is on, it tends to align along the spin current, the polarization of the spin, of the injected spin current. That's the minimum torque direction. And then once the current is off, it can then spiral off to the opposite state. That's a macrospin picture. Okay, it works a bit differently depending on whether you have a perpendicular system with perpendicular anisotropy or in-plane anisotropy, but roughly that's the idea. Okay. However,
I apologize to that. I have to tell something. So we are a bit pushed by time. So can you please summarize your presentation?
yes, so I will move forward. So of course, in real systems, then these effects have to be seen how they act on the propagation of domain walls. Okay, so the action of spin torques on domain walls is very important. I'll skip this. Okay, so this is how actual current-induced switching takes place in a cobalt dot on a platinum current line, and you see the nucleation of a domain, propagation of domain walls, and switching. And these effects can be used now to switch the state of a magnetic tunnel junction. Here, I just want to point out that one can switch the free layer of a tunnel junction using both a spin transfer torque as well as spin orbit torque. If you have current injection from the bottom layer or from the top layer, so and you can also combine the two. And this can also be assisted by voltage control of magnetic anisotropy that affects the coercivity of this layer. So this can actually be proved right now. These are current-induced switching curves measured in magnetic tunnel junctions by spin transfer torque only on the left and spin orbit torques on the right. There are some relevant differences in the dynamics, in particular in the switching times. And yeah, I will refer you to the papers. One important thing is that this current-induced switching, because the spin accumulation occurs in a non-magnetic conductor, can also be transferred to insulators. So if you deposit the platinum current line onto an insulating layer like a thulium iron garnet here, you can actually reverse the magnetization of the garnet underneath the platinum line, all electrically. These are movies, but no time to show them. Okay, and there is a whole field of studies of how one can use the spin orbit torques to drive magnetic domain walls, and also, for example, as in this case, one can drive domain walls in racetrack structures that have also competing interactions in terms of magnetic anisotropy and Jaruzelski-Marie interactions. And one can fabricate logic gates that function based on the propagation and manipulation of domain walls. Okay, so I'm sorry for the extra time. What I wanted to say in this last part is that these current-induced effects are very powerful to drive fast dynamics in small devices. They can also be combined with each other, so the spin orbit torque, spin transfer torque, electric fields effect, and as well as heating, they can all be used in order to increase the efficiency of current-induced or electric field-induced switching. And this allows for fabricating all electrical magnetic memories. And they're also interesting perspective for so-called memory in logic applications by combining several effects together. Last, from a fundamental point of view, the spin charge conversion effects are really very interesting. They take place in essentially all kinds of magnetic materials, including insulators, including also 2D magnets, as well as antiferromagnets. And so this is really an interesting field of investigation that combines interfacial effects with non-equilibrium effects in many possible applications. So thank you for your attention, and I'm happy to take questions.
Okay, thank you, Pietro, for this nice illustrative presentation. You can see the applause from hubs. I may ask, I saw one slide that you had there pyramid, and you had there several sets of memories, and one of them was non-volatile memory devices. Please tell me some requirements which memory devices can be considered as non-volatile, and what parameters are the crucial for this division.
Mm-hmm. So, I mean, non-volatility depends on which timescales we're interested in, and this can vary from memory to memory. Right? For long-term storage applications, the usual stability criterion is 10 years or more. Also, including some temperature considerations, right? So for mass memories like tape or hard drives, 10 years is considered to be the minimum. But if you go to random access memories, then it doesn't need to be as long, because typically you don't keep a computer on for 10 years at a time. So then it depends a bit on really the applications, on the data retrieval rates. But still, even for magnetic random access memories, people tend to think of strong, long retention times. And that is true also for non-magnetic type of memories, like ferroelectric memories or flash memories, etc. However, for certain computing applications, then maybe retention times of seconds would be enough. This really depends on the application. But the usual figure of merit for magnetic tunnel junctions is, so we want a stability ratio. So this is a ratio of the magnetic anisotropy energy barrier for switching related to the thermal energy KBT. This ratio should be larger than 50 or 60. Right? And that gives retention times of the order of years. Yeah.
Okay, thank you a lot. I can see there are two questions from Brno. So first one is, thank you for a nice comprehensive lecture. In a system featuring spin Hall effect like PT, FM bilayer, is the spin accumulation in the PT proportional to the PT film thickness? How about the efficiency of the interfacial SOT as a function of the ferromagnetic layer thickness? Okay,
so there are two questions there. One is, if you just consider platinum, okay, so you take a platinum film, you inject a charge current into this film, then this will produce spin accumulations at the edges of the film. In particular, for what I've shown is what matters is the spin accumulation on the top interface, right? So now this in a drift diffusion model, so in the usual model that one uses to discuss the spin Hall effect, then you need a certain thickness of platinum to allow for the spin accumulation to settle, essentially. Because otherwise you have back diffusion of spins from the interfaces, and the spin currents cancel each other. So it is typically considered that one needs a minimum thickness of platinum of around 3-4 nanometers in order to achieve a full spin accumulation. We actually think that in platinum alone, this should be larger, so the order of 10 nanometers, but this is debated. Okay. Then there are also, for example, ab initio calculations that show that the charge spin conversion efficiency, if you want the spin Hall angle in a metal like platinum, depends on the layer, how close the layer is to the interface, because the electronic wave function change, so also the charge spin conversion efficiency changes, and so you can have a enhanced conversion efficiency at an interface. This sometimes is described as a interfacial spin Hall effect. Sometimes is people prefer Rashba-Edelstein effect. In the end, these are two simple models, and none of them is appropriate to discuss what is going on in a material like platinum. The second question is, suppose you have a given spin accumulation at the interface of platinum, and then you place a ferromagnet on top of it. Then these non-equilibrium spins will diffuse into the ferromagnet and be absorbed. Okay, so this absorption depends on the thickness of the ferromagnet. Okay, so if the ferromagnet is too thin, you cannot absorb all the non-equilibrium spins, and so the spin torque, the spin orbit torque would be smaller. There is an optimal thickness in which all the injected spins can be absorbed. Okay. But if you go above that thickness, then the torque is still the same, but the magnetic volume that has to react to the spin torque is larger, and so the response of the magnetization is actually smaller, right? So that's why you cannot switch a 30 nanometer thick cobalt layer using the spin Hall effect of platinum. You can switch 3 nanometer thick cobalt layer, but not a 30 nanometer thick cobalt layer.
Okay, and please tell me what can be that typical thickness of platinum to get the highest efficiency.
It's typically is between 3 and 5 nanometers. You want to make it large so as to larger than the spin diffusion length, but you don't want to make it too large, because if you make it too large, then you're wasting a lot of current in the bulk of platinum, which does not produce any useful additional spin accumulation. And so there is an optimal thickness that is typically between 3 and 5 nanometers.
Okay, thank you. I have here the other question. What are the criteria for the associated activation energy barrier for magnetization reversal in terms of NP span, such as fine-grained and coarse-grained of atomic spins?
In that, I guess it goes to a non-macrospin picture. So then you have to see in an extended magnetic systems, right? It is most often the case that the magnetization reversal is not coherent, right? So it's not macrospin. So usually magnetization reversal starts where at those points where either the magnetic anisotropy energy barrier is smaller, can be due to let's say boundary effects, so geometry effects, for example, in elongated magnetic particles, or it can be due to defects. Okay. And then you have a nucleation of a reverse domain with a smaller activation barrier, and then the propagation of domains, the expansion of domains, driven by either field or spin torque or also temperature. Now, how this proceeds in practice is really system dependent. So there is, it depends on geometry, it depends on size, it depends on the distribution of defects. It depends also on the presence of non-collinear magnetic interactions, like the Jagosinski-Morier interaction is known to favor nucleation of reverse domains in certain structures. So this is very much system dependent.
So does it depends on the broken of symmetry rules, like defects and this criteria, the spin magnetization reversal and this defects? You said that defects plays a role in the this activation barrier mechanism energy calculation. So does it ultimately depends on the breaking of symmetry rules, like if we do the some kind of modeling of the magnetic reversal like that?
So these are two different things, right? You can have a defect, of course, a defect also breaks symmetry, but in the end, it is a local singularity where the, for example, the magnetic properties change. Typically, if you reduce the magnetic anisotropy energy at a defect, right, there it will be easier to start the reversal of the magnetization. Okay, but there is no specific symmetry rule to that. There are. It's easier to see symmetry-related effects when you consider, for example, non-collinear magnetic interactions. Then these are due to symmetry breaking, and so, for example, they're particularly strong at interfaces, or they're particularly strong at the boundaries of a magnetic structure. So there you have symmetry-related rules. And then you have geometry effects, like, for example, the demagnetizing field, right, is geometry dependent. Okay, so so in a way also dependent on symmetry. So all these effects play together, but there is not a single symmetry rule that is valid for all systems.
Yeah, I think I got the second answer, like next question answer I got with your, like I got answer of the next question. And the same question I have asked in the second question. So
sorry, I have to apologize, but we are pushed by time. I would like to thank all participants for questions to Pietro. We have still some of them, so I would like to ask Pietro if we can send them to your email. And if you're willing to answer us, we would be very happy.